my name is Oscar Carvalho. I'll do my presentation that is development of functionalized surface textures on zirconia for dental implants using laser. So this is the outline of my presentation. First, I will talk of my city, my lab, and then finally the focus of the presentation of this webinar. So my starting with my city. I'm from Portugal. That is set in Europe. From Portugal, and this is some nice cities and the place from Portugal if you want to visit. And this the place where my university is located. This is University of Minho. So talking a little about my lab, that is MEMS Group. Our MEMS Group is a center of micro electromechanical systems. So in our case, because there are different labs, we are working on the developing integrated smart components for biomedical applications and for other applications. In the case of biomedical applications, you work with zirconia and titanium substrates, PEEK. Also, we develop cellular structures, zirconia structures. Also, we work with the nanoparticles and smart materials like nitinol and the piezoelectric materials. So, this is just a small introduction of what our group is developing. So focus on the presentation of today. So we are developing functionalized surface zirconia for biomedical applications for different purposes, for bioactivity, antibacterial effect, fiber integration, electrostimulation, and communication systems. Today I will talk some work that I developed here in this part in bioactivity. Currently, there are different approaches to develop a surface for osseointegration to increase bioactivity. These are some commercial solutions using most of them use chemical treatment of the surface, all these solutions is to change the surface condition of the implants that have a big impact in the short term in the osseointegration, in the long term to keep the bone healthy. So we are working on this surface condition, working on surface of the implants. Why? Because these surface conditions affect the behavior of the cells, in this case of the osteoblast cells, that are cells responsible for the bone growth and osseointegration. And with this, because this surface change the interaction of the cells and the surface. So some properties of the surface, like the power, chemistry, potential, heterogeneity, change the interaction of the cells with the surface. So we are working on this surface. So these are some factors that affect the behavior of these cells, like biological effects, the substrate properties, and also the microenvironment. So, as I mentioned, there are different methods for this. There are subtractive methods like acid etching, alkali treatment, anodization, and also additive methods. Subtractive are methods for removing material. Additive are methods for deposition of material. For additive manufacturing, there are different approaches, additive manufacturing, that are different manufacturing process, like electron beam, laser, ion beam texturing, that's arc, many different processes. We are using this process that is laser. We are using laser because we're using laser, you can at the same time texturing and at the same time additive manufacture. So you can subtractive and at the same time you can develop additive process. To the people that didn't know what is a laser, laser is definition of this light amplification by stimulation emission of radiation. So this process, how it works, there is a medium where there is excitation of this medium, and using this transition between the electrons and there is a generation of a radiation, a beam, a laser beam. So this is more or less a resume of the process. So the interaction between the laser and the materials depend a lot of things. One of things is the characteristics of material, so the absorption of material, lasers, wave laser, the wave different wavelength lasers. So and also the laser, taking account how laser works. You can take into account power density and also interaction time. You have lasers for different processes, for ablation, macro machining that is used for subtractive process, and also laser for cutting, and also laser for additive manufacturing, also welding, as you can see here, welding. So depending of the power density and the interaction time, we can use the laser for different purposes. So I will talk about using laser for surface texture and laser additive manufacture. So I use laser also for subtractive and also for additive. Subtractive to remove material from the surface of the substrates, and additive to put material on the surface. So with the subtractive, what we perform is surface texturing. So you create structures for the next step, that is for additive. And with this, because with this surface subtractive, we promote structures that will help the addition of these materials that we'll put next. So with additive, we put material over these structures, okay? So we combine those process, both process using laser, and to produce multifunctional material components. So this presentation, this project was looking for is developing surface functionalized by laser in order to develop implants, and in order to evaluate the behavior of these implants, we perform some we are looking for some specifications, like implants should have surface wettability, mechanical strength, primary stability, and biocompatibility. So we will evaluate in this work. We will evaluate these specifications. So what we did was first we prepare the surface. After we make a characterization, first surface characterization. When you make a surface characterization, we perform some mechanical performance characterization, that is friction tests and wall entry tests. And also, if it's good, mechanical performance is good, we study the cell response investigation. So if it's good, we perform animal studies. Here I will not present these animal studies. So this is the layout, the workflow. What we perform first, in this case, you are using zirconia. We have these compacts. We make the laser texture using different topography, and also we sinter this. We sinter the substrates, and after we have bioactive materials that we sinter by laser. I'm presenting this too fast, but you can see the reference that I will put here in order to have more detailed information. So to perform the characterization, we make surface wettability, friction tests, and for mechanical strength, we use this test, ball entry, the B3B. To perform the samples, what we did, we put the powder inside a die, applied pressure, and we have green compactors. After we make a laser texture on these green compacts, using a laser with these characteristics, and then with these characteristics, that is here, the characteristics of laser, and then you have these parameters. These are some strategies that we perform the topographies. After you can see with more detail in this reference how we perform this. What we change here, the thickness of lines and distance between lines. So after we go to the furnace, we sinter the samples, and then we apply the bioactive materials. They are, in this case, is hydroxyapatite materials, could be other. To make the coating, in this case, we use bioactive coatings, already test also sprays and other techniques. Also, we perform wettability tests, and also we make friction tests where you use the samples against the bone. Why we did this? Because we want that the coating material resists to the friction force during the insertion of the implant. So also make the B3B tests in order to evaluate mechanical strength, and also evaluate the cell adhesion behavior. Okay. So some results here, we have the topography, some topographies that were generated using laser texturing, where we test different laser power and different drawings. Here another again, where we increase the number of passes. You can see here that we increase the depth of the texturing. Also, we perform sorry. Also, we perform surface wettability, where we can check there are many samples that they have are super hydrophilic samples, as you can see here by the water contact angle. Also evaluate the friction tests, where, as you can see here, the friction tests, you can see that during the friction, they are bond that is transferred. They are bond that is transferred to the sample, bond transferred to the sample. But we check that in the bond, that is the contact body, we didn't observe that is released bioactive materials. That is good. That is okay. The addition of the bioactive materials on the surface is good. Okay. So also we perform the B3B tests in order to evaluate the mechanical strength of materials according to the standard. For biomedical, for dental applications, the flexural strength should be higher than 1500 megapascal. So we have here some patterns that are feasible for the application. All these patterns are feasible. So at the moment, okay, you can choose these two patterns for the final application. They are these two patterns are not good. These patterns represent the condition of the deeper ones. Also, we perform the B3B. Also, this is again, I already talked about that. So also, here you can see some surfaces, some different surface where we sintering the material, the bioactive material, using different conditions of laser and velocity. Once again, here you have material. So in the end, we have the surface, texture surface covered with the bioactive material that was sintering by laser. Here you can see here a thin layer of hydroxyapatite coating. Here you perform also a characterization where you evaluate the ratio of calcium and phosphor in order to check if there is degradation of hydroxyapatite. As you can see, according to literature, when the ratio is, according to this ratio is good, okay, there is no degradation of hydroxyapatite. Also, we perform hydrophilic tests, I already mentioned. As you can see here, this is a surface where you can see the droplet layer we put, and you can see that droplet. You can see when I touch the sample in the liquid, you can see that this surface are super hydrophilic. Also, this is as already mentioned, the flexural strength is good for the application. Also, here you can see the cell viability tests. As you can see, the cells that cover the surface. Here you can see our conditions, where you can see that the viability, when you cover this, you have this is the surface with just the topography, and this is the surface with the bioactive materials. As you can see here, there's increase on cell viability. Here again, you can see here the surface covered with these cells, with the osteoblast cells. So, as you can see here, you have excellent and continuous coverage of cells along the surface. So all the process, as you can conclude at the moment, that this is a versatile process, or the process where you combine laser texture and laser additive manufacturing. What advantage of this is you can put materials in the place where you want. You can develop super hydrophilic and hydrophilic surface with enough strength for the application. Also, the laser sintering process of hydroxyapatite is a very versatile and promising coating technique. And also, as you see, the laser sintering maintain the bioactive characteristics of the coating. So, just for the conclusion of this part, as you can see here, this process where we combine laser texture with laser texturing, or say laser subtractive technique with laser additive technique, is a feasible technique to put bioactive materials over a surface of the implant where you can choose the place where you point material. So with laser, you can locate, you can choose the place where you sinter the materials. So you can find more detailed information in these papers that are already published. So if you want, you can look for this reference where you have more detailed information. Also, also we develop a functional surface in zirconia for other applications that I will not talk here, but I will just show the reference for antibacterial applications, fiber integration. For you are using the same technique, you combining laser text with laser manufacturing, but in this case to introduce nanoparticles, for instance, in the surface of the implant, nanoparticles and silver for antibacterial solutions. Why? Because dental implants need to have stability, osseointegration, but also because in the mouth there are a lot of bacteria. We need to have this antibacterial specification, because one of the big problems of dental implants and the other implants is the bacteria and formation of biofilm. When there is a formation of biofilm, the body rejects the implant. This is one of the main causes of the losing of the implants. So this is the case for the antibacterial, also for the fiber integration. Another approach to avoid the bacteria, it's here in the top of part of the implant, have fiber integration, where the gum cells can seal the implant in order to avoid that bacteria go to inside. So it is another application. You can see the refs and where you make laser text, and after you can see you can find more information about in this work. This is another way of avoiding that bacteria go to inside. And this you can also find here in this reference. So another application that we developed in functionalization of zirconia was for developing communication systems. What is this importance? We can imagine this is not a dental implant, but this is an hip implant, but could be dental implant, where we print in the surface of the implant circuits. What we perform by laser text, we make the cavity, and after by laser sintering, we promote the welding, we build a wire in these cavities. So we are printing circuits over a surface of the application over the implant, that it could be a lot of applications like communication systems, electrical stimulation, and etc. So you can find details information here. And also here you can some works related with this, related with what was I talking about. Also you can find in my scope if you want. So you also work with another materials, like you apply the same principles in magnesium, in titanium, and also in PIC, using the same principles. And also we apply the same approach for another applications that are no biomedical, like cutting tools, like piston rings in cars, like in polyamide. So yeah, using the same approach for a lot of applications, not only biomedical, but also non-biomedical. And also I like to thanks to some of these projects, to SMEMS groups, that is the group where I work, and also to the people, this interesting team, nice people that like to work, but also like to another more interesting things. And so if you have any doubt, please you have here my contact, and now I'm available to answer any question.